Let's look at this problem. Two right circular cones with vertices facing down, as shown in the figure below, contains the same amount of liquid. The radii of the tops of the liquid surfaces are 3 cm and 6 cm. Into each cone is dropped a spherical marble of radius 1 cm, which sinks to the bottom and is completely submerged without spilling any liquid. What is the ratio of the rise of the liquid level in the narrow cone to the rise of the liquid level in the wide cone? This problem is a very special application of the solid geometry or three-dimensional geometry, but the methodology to solve this problem is very standard. We just need the volume formula of this circular cone. But before we come to the formal solution, I want to introduce a very special way. Let's call that a quick and dirty, or maybe call that a very intuitive, informal way. It's not rigorous at all, but it can give us some insight about this problem. And very likely this insight will lead to a very quick solution. Alright, so let's get started. As we said, in the first method, we will think of this problem in a very special way. So we know that when we drop a marble into the cone, certainly the surface of the liquid will rise, right? And it will rise along this circular cone. So let's assume that in a very strange world, the rise of the surface is not along the cone. It's actually rising vertically into a cylinder shape. Okay, let's draw it out. So let's say it's rising like this, right? It's rising into a cylinder. Alright, then it's much easier to calculate the volume of a cylinder than the volume of a cone, right? And some students may say that, but that's not the right way, right? We will discuss that very shortly. And for the left cone, it will do the same. It's the surface is rising vertically and into a cylinder. Good. Then we know that for a cylinder, the volume equals simply the area of the base, that is pi r squared, times the height, the delta h. And we will do the same for the right cone and for the left cone. Let's start from the left cone. And that is pi times r is 3 cm, right? That's 3 squared times delta h1. That's the height of this cylinder. And for the right cone, we have pi times, the radius is 6 cm. That's 6 squared times delta h2. And now you may wonder, what's the relationship of these two quantities? As we know that the cause of this rise of liquid surface is because we drop a marble in it. And because we drop an identical marble into each cone, the volume of the cylinder should be equal. But you may wonder that this is not the right case, right? As you said, it is in a strange world. That's right. They are not strictly equal, right? Therefore, in here, we write they are approximately equal. And at the same time, we will mark the space that we left out, right? We'll mark that in the pink color. So this part and this part is left out, right? This part and this part. Good. Now let's come back to our equation or approximation. For this approximation, if we simplify that, we cancel the pi, we cancel this 3 squared with the 6 squared, and we have a 4 left. So delta H1 will approximately equal 4 times delta H2. Therefore, even though we are not accurate, but by checking this pink part, the volume that we left out is fairly small. It's very small comparing to the volume of the cylinder. Therefore, we should know that the ratio of delta H1 and the delta H2 should be in the neighborhood of 4. It should not be too far from there. Good. Now let's check the choices. So A, that's 1 to 1. So this is far off. That's certainly wrong. C, 2 to 1. That's still way off. And the same reason, B is out, because that's close to 1 to 1. As we said, it should be in the neighborhood of 4 to 1. Therefore, the only two choices left is D and E. And I can say that I'm very confident that E is correct. Why is that? Because let's look at D. Some students may say, D is very close to 4 to 1, right? So let's write it out. In order to make it a 4 to 1, it should be either 40 to 10 or 52 to 13. Depends on how you write it out, right? So these two equals 4 to 1. And even though choice D is close to 4 to 1, but it's still off by too much. Let's take this ratio for example. Let's look at 40 is good, right? The problem is 10 and 13. And they are off by 30%. At the same time, let's look at the pink part which we left out. That is like a ring of a conical shape, right? But don't forget, when we calculate the volume of that kind of shape, we have to multiply a 1/3, which is very different from a formula like a cylinder. For the volume of a cylinder, we don't multiply a 1/3. Therefore, we have a 1/3. And at the same time, let's look at this distance. This distance. That is certainly no more than half of this distance, right? In this scenario, this is 6 cm. This distance is very small. That's just the marginal part. Therefore, the volume of the pink part should be around, let's say, 1/4 of the 1/3 of the cylinder volume. 1/4 is from the difference of this radius or something, or the base, right? And when we calculate the volume, we have to calculate the area of there. So that has to be the square. So the relationship got to be a square of the length. And the 1/3 is from the formula when you calculate conical-like shape. Therefore, the part that we left over should be around 1/12 of the volume of the cylinder. And it shouldn't explain this difference of 30%. 30% is way too much. If there's a choice like a 40 to 11 or something like that, then it's hard to decide. But 40 to 13, that is way off our target, 4 to 1. Therefore, we are fairly confident that E is our solution. Good. So this is the insight about this problem. The elaboration of this thinking may sound very lengthy, but when you think about it in your mind, actually it shouldn't take you more than maybe 20 seconds or so. So this is a very quick and dirty way, and you should be able to get the answer E very quickly. Good. So now let's look at the formal way. How should we solve this problem rigorously? Let's browse down a little bit and erase all the mess in the diagrams, because we will reuse this diagram. Alright, in order to do that, we know that we have to use the formula to calculate the volume of a circular cone. Method 2. We have to find the relationships first. Because at the very beginning of this problem, we know that in each of the cone, there's the same amount of liquid already. Then we have to use this relationship. So let's put that into the formula. In the left cone, we have 1/3 of the area of the base, which is pi times 3 squared times h1. Let's call this height h1 and call this height h2. So in order to be consistent, for all the variables with the left cone, we'll have a subscription of 1. And for the left cone, we'll have a subscription of 2. Alright, this shall equal to the volume of the liquid in the right cone. So that is 1/3 times pi times 6 squared times h2. And we can easily simplify this to h1 equals 4 times h2, right? We cancel out this 1/3 and the pi, and we cancel out this 3 squared with this 6 squared. Therefore, we have h1 equals 4 times h2. And from here, do you recall what we said in the first method? Because intuitively, this 1 to 4 shall be our answer. But we are not done yet. This is just another evidence that proves our intuition. Okay, let's look at the next condition. The next condition in this problem is that we drop a spherical marble into each cone, right? As a consequence, the surface of the liquid will rise. So let's look at the right cone to illustrate that. The surface of this liquid will rise to here, right? Let's assume it's rising to here. And this is the rise of the height. So let's look at this part. Do you see this? This is a very interesting shape, right? So let's pull it out. Let's pull it out. It is something like this. And this is the new surface. And this is the old surface. We know that this line is parallel to this line. Good. And this shall remind you of some geometry facts. It can either be similar triangles. For example, the smaller triangle is similar to the bigger triangle, right? Or it can remind you of this intercept theorem. But in either way, we are going to use ratios. So let's say r is the radius of the original surface, and r prime is the radius of the new surface. And this is the original height, h, right? So this is a general diagram. It applies to either cone. And this is the new height, h prime. Now some students may wonder, why do we use a h prime? It's easier to understand that we have to use this r prime, or we have to use this r. Then why not we just use this delta? Because that is all what this question is asking about, right? My answer is that delta is not good. Because when we use this h prime, we can express this proportional relationship in a very clean way. It can be much easier for our next step derivation. So let's write it out. So from either similar triangles or from the intercept theorem, we shall have r prime to r equals h prime to h. And this applies to either cone. And since this is a ratio relationship, why not we set the ratio to k? Good. Then we have this general formula. Now let's look at the problem again. The problem says we drop an identical spherical marble into each cone. Therefore, the volume that the liquid rises shall be equal for both cones. So let's write that out. That will be the new total volume of the left cone, which is 1/3 times pi r squared. Actually, it should be r prime squared because the surface has rise. But what is r prime? R prime is actually k times r. And r is 3 in this scenario, right? And the k, we will use k1. So we will assume the ratio in here is k1. And the ratio with the right cone is k2. And we need to square this times k1 times h1. this is the new height, right? And the whole thing minus the original volume, which is 1/3 times pi times 3 squared times h1. So this is the volume of the marble. That should equal the volume change in the second cone. That is 1/3 times pi times r prime squared. And r prime is r times k, and r is 6 in this time. So that's 6 times k2. K2 is the ratio for the right cone. So this square times the new height, which is k2 times h2. And this minus 1/3 times pi times 6 squared times h2, right? So this difference is also the volume of this spherical marble, and they shall equal. Now we have this equation. So let's simplify this equation a little bit. It may look very messy, but actually we can cancel out a lot of terms. So first, let's look at the left-hand side. In the left-hand side, let's look at the first item and the second item. Let's compare them. So in the first item, we have a k1 square, and we have another k1, which is a total of k1 cube. And the rest of the first item is actually identical to the second, right? Therefore, we can factor that out. So we have 1/3 times pi times 3 squared times h1 times k1 cube minus 1. And we will do the same with the right-hand side, which is 1/3 times pi times 6 squared times h2 times k2 cube minus 1. And don't forget, we have this relationship. So we can cancel out all these identical terms. This is actually canceling with this because of this equation, right? Therefore, we have k1 cube minus 1 equals k2 cube minus 1. And that implies k1 equals k2. What does that mean? Okay, let's look at this. We'll write it out. Since k1 equals k2, right? So for the left cone, we have h1 plus delta h1 over h1. That is k1, right? Which equals k2 equals h2 plus delta h2 over h2. Is that right? So we can rewrite this as h1 over h2 equals h1 plus delta h1, h2 plus delta h2. So they are the same. Therefore, by taking the difference of the numerator and the difference of the denominator, we have delta h1 to delta h2 equals h1 to h2, which is 4 to 1. Therefore, the answer is still E, which justifies our intuitive thinking, 4 to 1. If you like this video, please give it a like and subscribe the channel. If you have questions, please leave a comment.